Hello everyone. So what we're going to do is we are just going to review some stuff for our test. So what we're going to look at first is we are going to look at the Le Chatelier's principle. So let's just go over, I'm getting my thing hooked up, sorry. Go over practicing where the shifts are going to be, right? So you have equilibrium, right, of an equation, and we talked about it. It's dynamic, right? It's not stagnant. It's not like, remember, I always think of the highway. It's not like those cars are just sitting there, right? They're constantly moving, right? But you have that equilibrium that at any given point, right, you have whatever that ratio is of the concentrations, and if you add in products, well, where's that shift going to be to reestablish that equilibrium? If you add in reactants or take them away, if you have an endo or an exothermic reaction, if you add heat, pressure, right? So all of those different things affect the equilibrium and the shift where that stress is going to cause the shift to go. So let's just do some practice here. I got that. Let's get some pen tools. Okay, so the Chatelier's principle, when a system is at equilibrium and it's subjected to a stress, it's going to shift to relieve that stress, right? Just kind of in life, right? We get stressed, we find out what we want to do to not be stressed. So in the chart, right, left or right for the shift, and then what happens to the concentrations. We're not going to worry about this right now. So we're just going to focus on the shift. So here in the first example, here's our equation, right? Ammonia, creating ammonia. So if you add N2, so if we add a reactant, where's the shift going to be? Well, it's going to shift towards the products, right? It's going to shift towards the right. So then what happens? Well, if it's shifting towards the right, towards the products, you're going to have a decrease in a reactant, right? This is a reactant, and you're going to have an increase in the product, okay? So let's do the next one. We add H2. Well, again, same thing, right? It's a reactant. So we'll have a shift to the right. What happens to the N2? Well, it's shifting towards the products. So that means that the reactants are going to decrease, products are going to increase. If we add NH3, which is a product, and I'm just drawing arrows, we're going to shift towards the reactant. So we're going to have an increase in the reactants, right? And then the shift is towards the left. Remove, so if we remove a reactant, it's going to shift back towards those reactants to reestablish. So we would have an increase in the reactants, decrease in products. Same thing, it's a reactant. Remove H2. So we'd have a shift towards the reactants. So we'll increase reactants, decrease products. Remove NH3. So if we're removing a product, where is it going to shift? It's going to shift towards the product. So we'll have a decrease in reactants. Increased temperature. So notice here, we talked about this in class, plus 22 kilocalories. The way this is written, it means that heat is a product. So if heat is a product, we have an exothermic reaction. If it had delta H equals plus 22, that would mean it's endo. But we don't have that, so you have to make sure you know how to read these equations. It says plus 22 kilocalories. That means it is a product and it is an exothermic reaction, so treat it just like a product. So if we increase temperature, we increase the products, we would have a shift towards the reactants, we would have an increase in reactant concentrations and a decrease in product. Decrease the temperature, treat it just like a product. So if it decreases a product, we'd shift towards the products. We'd have a decrease in reactants and an increase in products. So now let's look at pressure. Remember, pressure is all about the moles, right? We have a 1, 3, so we have 4 moles as reactants to 2 moles products. And remember, the moles is the coefficients there. So we have 4 moles to 2 moles. So increase the pressure. So if you increase pressure, right, you're decreasing the volume. So I always picture that. So if I'm getting less and less room, how am I going to establish equilibrium again? Well, I need to shift towards the less number of moles, right? There's not as much room. So we need to, like, I don't want to say condense, but condense into the less number of moles. So we would have, if we increase pressure, if we increase pressure, we're going to go towards the less number of moles. So we're going to go towards products. So we would have a decrease in the reactants and an increase in the products. And then the last one, decrease pressure. So if we decrease pressure, we're increasing volume. So we're going to shift towards the bigger number of moles, right? So we'd have a shift towards the reactants because there's 4 of those. So decrease pressure, we'd shift towards the reactant. So we'd have an increase in reactants and we'd have a decrease in pressure. Okay, so that was review for Le Chatelier's. And now let's go on and let's review entropy, Gibbs free energy, that kind of stuff. Okay, so now let's talk about spontaneity, entropy, Gibbs free energy. So let's review here. Hold on, let me open this. Okay, so sorry, I want to make it bigger. All right, so we have our Gibbs free energy, right? Delta G is equal to delta H minus temperature delta S, right? So we have our Gibbs free energy, and if our Gibbs free energy is negative, things will be spontaneous, right? For our enthalpy, we know if it's negative, that means exothermic, which it favors, right? And then we have our temperature, and then we have our entropy, right? This is our entropy. And our entropy favors disorder, right? So it favors positive. So our entropy favors positive. Our enthalpy for spontaneity favors exothermic. So if you have a negative, minus, whatever these positives are, our Gibbs free energy, if it's negative, then it's going to be spontaneous. So let's look. True or false, all exothermic reactions are spontaneous. Well, if we look here, right, it's not just the exothermic. It favors it, but it doesn't, that's not the only thing that it involves, right? It involves the temperature and the entropy too. So if we have a small enough temperature and our entropy, we actually can have a non-spontaneous reaction even though it's exothermic. So this is false. Not all exothermic reactions are spontaneous. All right, circle the correct words. Nature tends towards higher or lower energy and more order or more disorder. So when we look, Gibbs free energy right here is, sorry, got things popping up here. Gibbs free energy, negative, right? So negative value. So nature tends towards lower energy, right? Lower energy. And then more order, disorder. Remember, entropy, more disorder. So it favors more disorder. We want the entropy. Remember, when you drop I always think about dropping the pencils. You drop the pencils and they get disordered. And lower energy. So lower energy, more disorder. All right, so which state of matter has the highest entropy? So has the highest disorder? Solids, I don't know where I'm at here. Solids, liquids, gases. Hopefully you're saying gas, right? Good. So most disorder, gases. Predict whether entropy change will be positive or negative for the following. Okay, so the first one, remember, entropy is disorder. So we're going from a gas to a liquid. Gas to a liquid, so it's going to have more order. So it is going to be what? For the entropy, more order. Solid to a liquid. So, sorry, more order is negative, right? Less disorder, negative. More order, less disorder. All right, so the next one, we're going from solids to liquids to gases. So it's getting more disordered. So it's going to be positive, right? Increase in entropy, increase in disorder. So then we have gases. Remember, pure liquids don't count. Remember that? So we're going from a gas to liquids. So gas to liquid, more order, right? So less disorder, so negative. Solid to aqueous. So we're going more disorder. Solid to solid, so temperature change. So we have a temperature change of 100 to 25. So we are going negative, right? We're getting more order, so less disorder, negative. And then we have gases to gases, but we're going from 2 moles to 4 moles, so more disorder, right? Negative, positive, negative, positive, negative, positive. Yep, check, we're good. All right, so don't get those confused. Entropy is disorder. So positive means more disorder. Where is my thingy here? All right, if a process is endothermic, and the process creates more order than existed before, the process is always what? So it's endothermic. So delta G, delta H would be positive, minus your temperature times it created more order. So times a positive. So positive minus a positive. The process is, so we want Gibbs free energy to be negative, right? All right, sorry, I found my mistake. I'm like, this isn't right. So it favors endothermic, which is positive, but it has more order. So it has a negative entropy. That's where I gotta like keep them in track. So entropy, disorder, positive is more disorder, and negative is less disorder. So it's negative. So you have a positive enthalpy minus temperature times a negative number. So positive minus a minus is a positive, right? So you're going to have positive and positive, which means Gibbs is going to end up being positive no matter what. So it will never be spontaneous because Gibbs needs to be negative, needs to decrease in free energy in order for it to be spontaneous. So don't forget, write the stuff down. Like even I got to think about it. Wait, what? Wait, it got it backwards again. So write it down, hash it out, think through it. All right, which of the following reactions will have an increase in entropy? Choose all. So an increase in disorder. So we want positive. So we're going from gas to gas. We're going from 1 mole to 3 moles. So A will have an increase in disorder, right? It increased in moles. B went from a liquid to a solid, right? It's not increasing in disorder. C, a liquid to a gas, for sure. And then D, let's see, a liquid to gas. Yes. So I think we're good on that. Let me make sure. So let me know. Yep. Good, good, good. All right. Let me know what questions you have. That was a good review for your learning check today and for your test. Well, your 5.13 learning check and your 5.14 test. So good luck. I know you'll do great.